DIENES, the topic of organic chemistry subject. Content of this topic includes introduction of dienes, structure, stability of dienes, preparation of diene, reactions of diene. We will see detailed reactions: Diels-Alder reaction, electrophilic addition reaction, and free radical addition reaction. Dienes are hydrocarbons, having two carbon-carbon double bonds. Synonym is Alkadienes. General formula is CnH2n-2. Diene shows nomenclature similarity with alkene. For a compound with two double bonds, the ane ending of the corresponding alkane is replaced with diene. Diene shows general formula similarity with alkynes, thus isomeric with alkynes. Dienes can be assuming as alkenes that contain two carbon-carbons double bonds. Dienes are divided into three classes, according to the arrangement of the double bonds. Classification of dienes: cumulated, conjugated, and isolated dienes. If double bonds are present on same carbon, that is, double bonds share a carbon, are cumulated dienes, and the compounds are called allynes. Examples are buta 1,2-diene, and propadiene. If double bonds are alternate with single bond, are conjugated dienes. Example is 1,3-butadiene. If double bonds are separated by more than one single bond, we may also say as double bonds are separated by at least one sp3 carbon, are isolated dienes. Example is 1,4-pentadiene, 1,5-cyclooctadiene. Stability of dienes. Heat of hydrogenation reveals the relative stability of dienes. Recall that the most stable alkene is one that has less energy. Thus, it gives off the least heat when it is hydrogenated. So most stable alkene has less heat of hydrogenation. Let's identify heat of hydrogenation of different dienes. Here are reactions of 2,3-pentadiene, accumulated diene, 1,4-pentadiene, isolated diene, and 1,3-pentadiene, a conjugated diene. All isomers of pentadiene, when perform hydrogenation reaction, give same product, that is pentane. However, different types of diene give different heat of hydrogenation values. When we look on heat of hydrogenation values, least heat is released by 1,3-pentadiene, which is the example of conjugated diene. That means 1,3-pentadiene is more stable than 1,4-pentadiene and 2,3-pentadiene. Conjugated dienes are more stable than isolated and cumulated diene. So, conjugated dienes are more stable than isolated and cumulated diene, and this stability is due to resonance in conjugated dienes. Let us see the example of 1,3-butadiene. In conjugated diene, all are sp2 hybridized carbons, so their unhybridized p orbitals lie in same plane, that is, vertical to sp2 plane. Thus, overlap between p orbitals of C2 and C3 is also possible, as shown in orbital picture shown in next slide. That leads to delocalization of electrons, that is resonance. Delocalization of electrons generates various structures, which are called as resonance-contributing structures. Overall structure is represented with dashed line, where dashed line shows electron delocalization, and this structure is actually called as resonance hybrid. The resonance hybrid is the single representation of all possible resonance-contributing structures. Let's draw a delocalized pi electrons orbital structure of 1,3-butadiene. First, draw the skeletal of covalent bonding in 1,3-butadiene. Now add p orbitals perpendicular to sp2 plane and make 2-pi bonding by p orbital overlapping. We have seen that delocalization of electrons is possible. That leads to resonance hybrid. This delocalization of pi electrons results in overlap between p orbitals of carbon-2 and carbon-3. So, for unpaired p orbital electrons are delocalized among 4 carbons in 1,3-butadiene. Choose correct option for MCQ. For 1,3-butadiene there are blank molecular orbitals for p electrons. Answer is 4. Preparation of dienes. Dienes may have prepared from alkynes. Ethene, on treatment with mixture of cuprous chloride and ammonium chloride, dimerizes to vinyl acetylene, which yields buta-1,3-diene on catalytic hydrogenation. Catalytic dehydrogenation of butane, or 1-butene, on heating with alumina and chromium oxide at high temperature, result in the removal of hydrogen to give 1,3-butadiene. Industrial method applies. Catalytic transformation of ethanol into 1,3-butadiene. The dehydration of 1,4-butanediol can be carried out in the presence of concentrated sulfuric acid. Results in the elimination of water molecule to produce 1,3-butadiene. Dienes, obtained from petroleum crude oil, are produced as byproducts during thermal and steam cracking of crude oil. E2 elimination reaction of 3-bromocyclohexene produces 1,3-cyclohexadiene. Reactions of dienes we will see in detail are Diels-Alder reaction, electrophilic addition reaction, and free radical addition reaction. Diels-Alder reaction. The reactions of conjugated dienes with alkenes to form a 6-membered cyclic adduct is known as Diels-Alder reaction. Diels-Alder reaction is example of Cycloaddition reaction. Cycloaddition is an addition reaction in which a cyclic molecule is formed. S-cis conformation, that is, Double bonds are cis about the single bond. S means single. This S-cis conformation of diene prefers Diels-Alder reaction. An S-trans conformation is a little more stable than S-cis. However, the rotational barrier between conformations is low enough to interconvert rapidly at room temperature. Mechanism. The Diels-Alder reaction is like a nucleophile, electrophile reaction. The diene is electron-rich, and the dienophile is electron-poor. The Diels-Alder reaction is concerted reaction. Electron movement is concerted, with 3 pairs of electrons moving simultaneously. The Diels-Alder reaction is also example of 4+2 Cycloaddition reaction. Here, 4 of the conjugated diene and 2 of the dienophile electrons participate in the 6p electron cyclic transition state. The Diels-Alder reaction is type of 1 for addition reaction, as the sp2 carbon of dienophile adds to 1 for carbons of diene. Dienophile reactivity. The reactivity of the dienophile is increased if an electron withdrawing group is attached to one of its sp2 carbons. Example of reaction. Diene reacted with acrolein, gives substituted cyclohexene derivative. Acrolein is a highly effective, fast-acting dienophile because its carbonyl group acts as an electron withdrawing group. The carbonyl group of the dienophile withdraws electrons by resonance, so its terminal carbon has a partial positive charge. Thus, the electron withdrawing group makes the dienophile a better electrophile. Dienophile addition is Syn. Syn-addition is a reaction where 2 substituents add to the same side of a double or triple bond. Syn-addition is the evidence that the Diels-Alder reaction has a concerted mechanism. The 2 new carbon-carbon sigma bonds are formed in the same transition state. Diels-Alder reaction is stereospecific reaction. Stereospecific reaction is any reaction in which the stereochemistry of the product determined by the stereochemistry of the starting material. Substituents that are cis in the dienophile remain cis in the product. Substituents that are trans in the dienophile remain trans in the product. Example of such reactions is given here. You can use the reference link for 3D mechanism of this reaction. Diels-Alder reaction prefers endo product. The Diels-Alder reaction takes place in the endo rather than exo sense. Unsaturated, pi electrons rich groups in the dienophile, for example, in maleic anhydride, tend to increase rate of endo product formation. This is due to interaction between the pi electrons of the substituent and the pi electrons of the ring, which stabilizes the transition state. A substituent in the exo position cannot engage in such stabilizing interactions. Multiple choice question. Which of the following diene is most reactive in Diels-Alder reaction? Right option is B, that has S S-cis conformation. Prefers Diels-Alder reaction. The perfect orientation for a Diels-Alder reaction between the reactants is right option is diene should be S-cis and reaction endo-facing. Electrophilic addition reaction of diene. Let first see electrophilic addition to non-conjugated diene. Dienes containing isolated double bonds. The double bonds react independently, as though they were in different molecules. In this reaction, 1,4-pentadiene reacts with bromine. Both double bonds react for electrophilic addition independently, that form 1,2,4,5-tetrabromopentane. Electrophilic addition to conjugated diene. In additions to conjugated dienes, a reagent may attach itself not only to a pair of adjacent carbons, that is, 1,2 addition, but also to the carbons at the two ends of the conjugated system, that is, 1,4 addition. Very often the 1,4 addition product is the major one. Example, 2,4-hexadiene reacts with HCl, gives 2-chloro-3-hexene and 4-chloro-2-hexene. Reagent may attach itself to a conjugated diene, to the carbons at the two ends of the conjugated system. Identify the reaction involved from the following. Right option is 1,4 addition. Let's see mechanism of reaction. Step 1 is addition of electrophile to carbon-carbon double bond. Here, proton may attach to carbon 2 or carbon 3. If proton attached to carbon 3, there is formation of carbocation in carbon 2. If proton attached to carbon 2, there is formation of carbocation in carbon 3. The intermediate where positive charge is at carbon 3, because positive charge is generated adjacent to the double bond. This is actually an allylic carbocation. Now compare the stability of both possible intermediates. Practically, allylic carbocation is more stable than secondary carbocation. Thus, the products obtained from addition to conjugated dienes are always consistent with the formation of the most stable intermediate carbocation, an allylic cation. Reason of stability of allylic cation is the resonance that cause interchange of positive charge between carbon 3 and 5. Step 2 is attack of chloride ion to the positive charge containing carbon. Due to the resonance, the positive charge is distributed at both carbon 3 and 5. If chloride ion attacks to carbon 5, this gives 1,4 addition product. And if chloride ion attacks to carbon 3, this gives 1,2 addition product. Explanation of mechanism. Step 1 is addition of electrophile to doubly bonded carbon. Formation of carbocation. Addition may occur into carbon 2 or carbon 3. Both conditions create secondary carbocation. But below 1 is allylic cation, formed predominantly because of resonance stabilization of allylic cation. Step 2. Attack of chloride ion to carbocation. As in contributing structure, carbon 3 and carbon 5 both have equal distribution of positive charge. Equal chance of pathway 1 and pathway 2. Attack of chloride ion at carbon 3 gives 1, 2, and attack at carbon 5 gives 1 for addition product. 1, 2 versus 1 for addition. For electrophilic addition to conjugated diene. 1, 2 versus 1. For addition is the theory of rate versus equilibrium. Kinetic and thermodynamically controlled reaction. Addition of hydrogen bromide to 1,3-butadiene yields both the 1, 2 and the 1 for products. The proportions in which they are obtained are markedly affected by the temperature at which the reaction is carried out. Reaction at a low temperature yields a mixture containing 20% of the 1 for product and 80% of the 1,2 product. Reaction at a higher temperature yields a mixture of quite different composition, 80% of the 1 for product and 20% 1,2 product. More 1,2 product is obtained at -80 degrees Celsius. Indicates that the 1,2 product is formed faster than the 1 for product. The 1,4 product predominates at high temperature indicates that it is the more stable than 1,2 product. When we go through the mechanism, there is reversible steps between 1, 2, and 1 for addition. Both allylic halides products readily undergo heterolysis that yields the same carbocation. The 1, 2, and 1 for products reach equilibrium is through this cation. Let us examine the matter of 1, 2, and 1 for addition more closely by drawing a potential energy curve for the reactions involved. The carbocation initially formed reacts to yield the 1, 2 product faster than the 1 for product. Consequently, the energy of activation leading to the 1, 2 product must be less than that leading to the 1 for product. Therefore, there is the lower Hill and low activation energy to form the 1, 2 product. The 1 for product is more stable than the 1, 2 product, and hence we must place its value at a lower level than that of the 1, 2 product. Rate versus equilibrium. At low temperature, the isomer predominates, which has high rate of formation. Here, 1, 2 addition product predominates at low temperature. So, 1, 2 product is formed faster. At high temperature, equilibrium between two isomers, isomer predominates, which is more stable. Here, 1 for addition product predominates at high temperature, so 1 for product is more stable. The proportions of products actually isolated from the low temperature addition are determined by the rate of addition, whereas for the high temperature addition, they are determined by the equilibrium between the two isomers. Free radical addition of dienes. Conjugated dienes also undergoes free radical addition reactions when the reactions are carried out in the presence of organic peroxides, light air, or sodium, to form 1, 2, and 1 for addition products. 1 for addition occurs predominantly. Example: buta 1,3 diene reacts with halogens in presence of an organic peroxide or light to form 1, 2, and 1 for addition products. Polymerization of buta 1,3 Diene occurs in the presence of organic peroxide or in the presence of sodium to give a rubber-like product. Mechanism. Step 1. Chain initiation step. That is peroxide homolytic decomposition and the formation of radical. Formation of phenyl radical. Carbon-chlorine bond is stronger than carbon-bromine bond. Thus, phenyl radical abstract bromine from BrCCl3. That generates trichloromethyl radical. Step 2 is the addition of free radical to carbon-carbon double bond. Here, allyl radical is formed predominantly due to the resonance stabilization of allyl radical. Now step 3. Formation of 1, 2, and 1 for addition products. Attack of bromine to the carbon radical. Due to the resonance, the radical is distributed at both carbon 1 and 3. If bromine attacks to carbon 1, this gives 1 for addition product. And if bromine attacks to carbon 3, this gives 1 to addition product. End of the topic of dienes. You may refer to these mentioned books. Organic Chemistry by Morrison and Boyd. Organic Chemistry by Meta and Meta. Organic Chemistry by Paula Bruce. Note down study questions related to this topic. Thank you.